is definitely a presentation that you don't want to miss. With that, I'd like to introduce again Satoshi Matsuoka from Tokyo Institute of Technology.
Okay, everyone, welcome to SC. I serve as the program chair for SC this year, so I hope you like the tech program. Now today, my intention is to tell you about being green and how GPU would help supercomputing to be extremely green, because being green is now the most significant parameter in the future of supercomputing. And I'll show you later how green we are with respect to our achievement on the Green 500. Okay, very brief intro on Tsubame 2, which is our supercomputer. Or was it slow? Tsubame was born in 2010. It's built out of massive amounts of GPUs and CPUs, and we co-designed the system with companies like HP, Nvidia, and so forth. It was the first petascale supercomputer to go live in Japan. The reason, of course, we use GPU, maybe it's old news, but because we figured out after some years of research that GPUs have very high performance in terms of power efficiency, both computational and also memory bandwidth. In fact, same generation of GPUs versus CPU, we were typically seeing about a factor of 5 improvement. So we work with Nvidia, of course, and companies like HP to create an infrastructure and a node to actually allow us to package the GPUs in an extreme high density. So when Tsubame 2.0 went live, actually we became the #1 supercomputer in the world, besting the combined performances of all other supercomputers in Japan combined. Tsubame has won many awards. In particular, in 2010, we became the greenest production supercomputer in the world. We're not #1 overall in the Green 500, but we were the only production supercomputer high on the list. Of course, we were #4 in the top 500, and we sustained that for a couple of years. In 2011, we won the Gordon Bell Award for this application, which not only solved this very important scientific problem of metal crystallization, but also achieved 2 petaflops in this application, and using 4,000 GPUs, which was, of course, a great achievement at the time, but also allowed for the first time the scientists to see 3-dimensional formulation of metal crystals, which you cannot really see visibly because it's metal, and scientists are only able to simulate this at scales that were insignificant. So Tsubame has several key applications that are of concern to mankind, of course, the taxpayers: disaster, safety, environment, medical, manufacturing. So one application done by one of our scientists is to simulate the entire Tokyo airflow in 1 meter resolution. 1 meter between you and you. Just 1 meter. But that's entire Tokyo, 100,000 times bigger than this floor space. Okay? And these are the results. These are accurate results of 1 meter resolution airflow. We got all the topological maps, the buildings. If you ever been to Tokyo, it's very complicated. But we can do exact airflow with exact turbulent physics. Actually, when you have skyscrapers that you have in like Tokyo, New York, Chicago, Beijing, then you can see that the airflow is very complicated. Sometimes you see airflow going up. And for the future city planning, pollution control, predictions of when a nuclear accident happens and you get pollutants, you might think get contaminated at certain hotspots. These kinds of simulations are utmostly important. But now we have the ability and the fidelity to be able to predict these. We can apply the same technology to automobiles. We can do exact turbulent flow simulation, of air that would be extremely turbulent at the very rear of the car. So, all the virtual wind tunnel pictures you see with very smooth curves, they're not correct at all. Actually, the air becomes very turbulent because of the little projectiles that starts the turbulation, but it magnifies it gets the rear cart. This is a 3 millimeter resolution, and with turbulence, which has not been achieved before. We can simulate earthquakes, and this is very important for Japan. And this is the simulation of the next possible big earthquake. And Tsubame has contributed to creation of a national hazard map because we were able to do very accurate predictions of earthquakes and what effect will it have to cities like Osaka, Nagoya, which will be affected by the next big earthquake. We have lots of industrial users, 140 companies in total. This is a TOTO, which is one of the most famous toilet bowl companies in the world. And they have used Tsubame to design very water-efficient toilet bowls, which is very important for countries like in the deserts that do not have abundance of water. So you need minimum amount of water to be able to cleanse your toilet. But what they have been able to achieve in the older simulation, it may look picturesque in terms of the graphics. So if you're shooting a Hollywood movie, this is okay. But in terms of physics, this is completely wrong. Whereas on Tsubame, they were able to simulate accurate physics. And this is a very complicated physics because it's a multi-phase flow problem with very complicated boundary conditions. So now TOTO is starting to design toilet bowls using supercomputers. We can have important pharmaceutical applications, drug design. Some of the diseases, like tropical diseases, often neglected because they are not very profitable to pharmaceutical companies. But with the global warming, we see these mosquitoes migrating from the south. So, places like Florida, Hawaii, Taiwan, Okinawa, also Japan, will start seeing this soon. I mean, that's what the scientists predict. And since it takes 10 years to create drugs, it's very important that pharmaceutical process be accelerated. And we have signed a contract with Asteris Pharmaceutical, one of the major pharma in Japan, to do actual drug creation. This is not a test lab thing. It's real drug creation process. And we can accelerate drug creation process by various means, molecular dynamics, also big data database searches of articles by factor 10 using these methods. So because of all this success, Tsubame became very busy. It became a very popular machine. So we were obviously in need of an upgrade because the machine was simply filled up. We couldn't satisfy the needs of these important applications. So what we would work with Nvidia and HP and NEC to do was to upgrade the machine. So to replace all the Tesla's Fermi with the Kepler, which is not a trivial task. It's not like you can go to Fry's or in Japan it would be Akihabara, just buy your own GPU, plug it in, replace it, plug it in. It doesn't work that way with a 4,000 GPU supercomputer. So it was a very long process. There are a lot of modifications that had to be in the node. We had to confirm that the performance of scale. We had to confirm it would be a stable operation even if we replaced the GPUs. We had to go through a lot of technological engineering challenges to overcome the difficulties. But nonetheless, we achieved that. And now, Tsubame, each of the node is a 4 teraflop node with almost a terabyte per second memory bandwidth. So we doubled, tripled the performance. We have much bigger capacity in GPUs, higher reliability, actually lower power. Despite the fact we doubled, tripled our performance, we're seeing lower operational power. And of course, with all the new Kepler features, we get better programmability and extended the life of the machine by almost 1.5 to 2 years. I'll skip the specs. But so now, Tsubame 2 in single precision is a 17 petaflop machine in single precision. Only 5.7 in double, which means that in single precision arithmetic, we're faster than the K computer. Unfortunately, not in LIMPAC, because LIMPAC is double precision. But we're the fastest supercomputer in Japan under this metric, and we're a hell of a lot smaller. And but these kinds of catalog specs will not matter if we don't scale to real if this doesn't apply to real applications. And in fact, they do. We have tested these major applications we have. They have seen consistent speedups. Now, at the 2 petaflop Gordon-Bell application is now approaching 4 petaflops. In our test, the CDF flow simulation you saw was about 0.6 petaflops. Now it's twice the performance. And also molecular dynamics, well, we had to use 4 nodes with 8 GPUs, leaving 1 GPU idle to achieve 3 nanoseconds per day. Now with a single Kepler on a node, we can almost achieve the same execution speed. So it's been quite consistent that we got over factor 2 to factor 3 across all applications, and also had about 10 to 20% reduction in operational power. So with that, we're heading towards 3.0. 3.0, so we were Tsubame 1. The first GPU was Tsubame 1.2. 2.0 was a first petaflops machine, upgraded to 2.5, 5.7 petaflops, and in 2015 to 16, we'll be going to 25 to 30 petaflops. But it's a big challenge because unlike other centers, we cannot increase our power budget or footprint. So you cannot say, well, we use 20 megawatts or use 30 megawatts, okay? Oh yeah, I'm going to double my performance, I'm going to double my electricity bill. I can't do that. Okay, it's not, so despite being on one of the fastest supercomputers in the world, we're very resource constrained. And one of the big resource constraint is power. And of course, there are lots of other things. We got to cope with new memory systems. We got to cope with new networks. Now we have to accommodate big data or I/O-intensive computing. More components system, we have to cope with fault tolerance. We got to be able to do better programming because we'll have millions of cores and machines. These are all the research subjects that we're tackling. But in the interest of time and also subject matter of this talk, I will concentrate on green. So how much greenness does it buy? So we had a project, ultra low power, HPC, in which we tried to look at, review all the components that constitute supercomputers and how green they can get. Look at applications, how green they can be made, how we would be able to auto-tune the parameters, combine parameters to be able to achieve factor of 1,000 in 10 years, which is by and large what you would need to sustain the growth that we've seen, for example, in metrics such as the top 500. Factor 10 growth and 1,000 growth in 10 years, which is well beyond Moore's law. Okay, so how to achieve this? Well, after all the years of research, well, the process shrink to Moore's law will probably give us about 100. And being many-core, using many-core usage, like I said initially, may buy us up for 5 if we develop algorithms to make use of the hardware architecture resources. Other metrics such as dynamic voltage scaling and tuning for low power, right? We don't shoot for the highest performance. We shoot for the best energy or power metric will get us another 50%. And new, more aggressive, efficient cooling will buy us about 40%. So all these combined, if you do the multiplication, you get a factor of 1,000. But can we do this? Are these numbers real? So in our project, we did lots of research to implement all of these factors, new algorithms for GPUs, various types of monitoring control algorithms and systems, new cooling, new architectural, various types of innovations, and which allowed us in a prototype, this is our prototype, to achieve extrapolated about 1680 improvement in the Dandrid application I just showed you compared to what it would have performed on the initial Tsubame in 2006. So this is the factor of 1,000 in 10 years. You'll see that the blue line, you get this huge jump because we go to many core. But then we will be pretty much safe until about 2018 here, such that we do get this extrapolated factor of 1,000 in 10 years. But this is, but as you can see, this is a very small test bed. It's a whole bunch of GPUs and motherboards configured with in a very green fashion and submerged in warm oil, using in collaboration with Green Revolution Cooling. But this is a very small system. How does it translate to bigger systems, and how to prototype with Tsubame 3.0? Okay, so now we got some money from the government, and then we configured a whole bunch of servers, put in the rack. In a single rack, we put in 160 GPUs, K20Xs. And we have a new, sort of like a sideways Green Revolution Cooling, oil-cooled rack. We put in the control system. We have the heat dissipation through the cooling tower. We don't use chillers anymore. The oil is kept at about 25 to 35 degrees, same as the ambient temperature, and then housed in a test facility, which is a 20-feet container with lots of little ingenuities to support these kind of infrastructure. The total peak of this single rack machine, it's 40 nodes, and one just about 40 U sideways, is 200 teraflops. And the single precision, it's like 630 teraflops. So it's achieving, in single precision, it's approaching half a petal. It's beyond half a petaflop. So we built this test site, and then we applied some of the technologies we developed in the previous project in order to tune for power efficient operation. So this is it. And then we tested our Green 500. So this is the Green 500 list from last year. I'm sorry, this year, but in June. So number one was Seneca using Eurotech machine. They were using Kepler's that achieved 3.2 gigaflops per watt, which is about that. DOE Exascale target is 50, so it's a little far off, but certainly it's very good, because compared to what the greenest supercomputer, production supercomputer back in 2010, Tsubame 2, was only 958.35 megaflops per watt. Okay, so compared to that, the Eurotech Italy Seneca Italian team achieved about over 3 times jump in about 3 years. Okay, where's Tsubame 2.5? Okay, before showing the caves, by the way, the facility is called Tsubame KFC. And KFC doesn't allude to big American food chain. But Tsubame, by the way, for those of you who don't know Japanese, it's a bird. And this is oil, and it's warm. Okay? But again, it doesn't allude to an American fast food chain. It's Kepler fluid cooling. I mean, that's the official designation. Okay? So Tsubame was here. Where is Tsubame 2.5? Okay, first I'll show you that. 2.5 is 3,068.71, which is a little worse than Seneca, the last. But this, remember, this is a production 6 petaflop supercomputer. With all, you got to have more memory, you got to have I/O, you got to have all these extra stuff. And this is a retrofit. Okay, it's not a brand new system. It's a 3-year-old system retrofitted with new GPUs. Will still achieve almost the same performance as the #1 machine, and in fact it'll be number 3 in the June time frame. As these little systems that were little systems, experimental, much as KFC was, that were ranked very low in the top 500, and thus, actually, from the next Green 500, they'll disappear from the list. So where is KFC? KFC achieved 4,511.86 gigaflops per watt. This is almost 50% higher than the previous #1. So the Green 500, which will be announced tomorrow at the Mile High Ballroom. Okay, Wednesday, 5:30. there's a very, very good chance that we'll be number one in the world. Okay? So, and we're still midway. So from Tsubame 1, Tsubame 2, K-Computer, Blue Gene Q, we've been making steady progress. These numbers include cooling, so they're a little worse off compared to the Green 500 numbers. But certainly, we have achieved about factor 30 in Tsubame 1 and even factor 100 compared to the original machine. Tsubame 3, we expect to improve this number by several, or if not order of magnitude, but by several factors, which is getting awfully close to the Exascale target. Because if we achieve our target in 2016, about 10 to 13 gigaflops per watt, we'll be only a factor of 5 off. So, and also in terms of the memory bandwidth per watt, we'll be very close to the Exascale target. So where does this greenness come from? It comes from the use of many-core, power-efficient architecture like GPU, and the ability of our system software tuning and application to be able to exploit the architecture. And then to formulate a machine, the entire architecture to exploit the greenness as provided by the GPU, which is the color of Nvidia. So with that, I conclude my talk. Tsubame 2.5, we became number one in Japan. Now it's 17 petaflops, fastest single precision floating point. 3.0 early, it'll have lots of new features, greenness, but also many other features, innovative features. With lots of background R&D for Tsubame, including big data, which I hadn't had the time to show you. But in terms of green computing, we are achieving and, in fact, exceeding our initial target. With that, I'll conclude my talk. Thank you very much.
Thank you very much. Do we have any questions here in the theater? Now that we all know what KFC stands for, I guess that question isn't going to be asked.
Yes. I don't want to violate copyright, trademarks or copyrights.
We do. I'm sorry. Go ahead.
Yeah. And yeah, so we have Tokyo Tech as a booth right near the K-Computer. I forgot the booth number. What was the booth number? Saito-san, what's our booth number? What's our booth number? You don't remember? Okay. Well, if you go to the back, you'll see a balloon that has a Tsubame logo on it. Okay. It has a Tsubame Tokyo Tech, but it's very visible. It's on the left-hand side of the sign-up booth. So you'll see that. So if you 1741. Thank you, Akiyama-san. 1741. So if you're interested in details, please visit our booth. That's 1741.
And before you all go to visit the booth, we do have a question from online.
Okay.
So I'm going to ask, the question is OpenACC the primary parallel programming solution used by users of Tsubame?
It's not the primary, but it's being used more in increased fashion because we're part of the OpenACC consortium. We're a member. And we work with various vendors. We have people who work with the compiler team to improve the specs and also to provide a lot of feedback of how they may not be doing quite the right compilation or doing the right runtime. And we have a number of papers regarding the OpenACC. And we have a program to have people with existing codes to help them port over to OpenACC. So it's increasing. We believe portability is a must. Of course, people with utmost performance-conscious mindset may use CUDA. But however, we are advising people to look at OpenACC as at least their initial porting target. If they like it, we would help them to tune it and continue usage. Yes.
Okay, great. And one other question, actually,
yes.
I had it as well. Do you have any preliminary results? I saw K20s were being used. Do you have
K20Xs, yes.
Do you have any K40 preliminary results?
We don't have K40 results because we don't have one. Because every time we do these, because these supercomputing experiments take hundreds of thousands, right? So getting, for example, Tsubame 2.5 was upgrade was quite a substantial acquisition process. So, but a K40 and beyond, Maxwell, We have high expectations for those architectures. They'll be several times more power efficient. And we're working with vendors, other vendors like NEC, HP, Cray, and to look at what would be the best architectural wrapper around it in order to best exploit its efficiency. So 3.0, all the work on 3.0 is focused around that.
All right. Well, thank you.
Thank you very much.
Thank you here.
And enjoy the rest of the conference.
Yes, and thank you for an amazing SC